Okay, so yeah, just a couple of things. If you saw the announcement, so basically, think I couldn't give you office hours earlier before class today. I just made the quiz for today like an assignment. So just like the announcement for the two problems, you can upload it, the solutions to Gradescope as usual, until tomorrow. So if you are stuck or anything, you can email me if you have any questions about the quiz problems. I also will add some more problems to the PDF. I'll try to get to that over the weekend. Um, yeah, so once I have that updated, I'll also let you know about that as well. Okay, so today, yeah, so today we're going to, I think it's kind of useful to start with an important concept called entropy, uh, because it's an extension of the way we have computed probabilities. So I'm going to tell you about what's called the maximum entropy principle. Okay, so just as a background of what's going to happen, okay. So yeah, just to give you some background of what the idea is. So far, like if you remember, especially for the problems on the first midterm, right? Or these problems in combinatorics that we were doing earlier in the course. Um, when we were computing probabilities, we were using, I don't know if I ever gave this name to this idea, but we were using what's called like the principle of indifference. So for the problems about, for the problems which computed probabilities, um, in we were using like the what's called sometimes the principle of indifference. Okay, so the principle of indifference, what would say, like for example, is like, well, you just count the number of ways in which something can happen, right? So this is why we were so interested in counting things, right? In how many ways things could happen. So you would count the number of ways, the number of ways in which something could happen. And then if there's no reason to favor one outcome over the other, you just assign the same probabilities to both of them, right? And if no reason to favor one outcome over the other one, you would assign the same probability, right? You would consider them equally likely. So like the examples that where this is easiest to think of how we were doing this was like with rolling a die, right? So like for example, we're rolling a dice. Like here, like you have 6 outcomes, and if there's no reason to think that the dice, maybe if the weight is not distributed, like if there's no reason to think that the weight is distributed unequally, let's say the die looks perfectly symmetric or things like that. So there shouldn't be like a reason to prefer one outcome over the other. And so if there's no reason to prefer one outcome over the other, you would just say that each you had like a probability of 1/6 for each of the sides of the die to show up or to get that outcome, right? So there are no reasons to prefer one outcome over the other. We would assign probability 1/6 to each side of the die. But of course, like in many problems, like those questions became more interesting very quickly because it relied on counting in how many ways things could happen, right? So another example where we had talked about this was when you would roll 2 dice, right? So here's example 2, rolling 2 die. So what was how did we find the probability of getting an 11, right? Like say between the two, if you added the numbers that you get from each die, so what was the probability of getting an 11? Well, 11, you could think that you got 5 on the first one, 6 on the second one, right? Or 6 on the first one, 5 on the second one. And I think, right, you need at least, those were like the only 2 ways to get 11 when you roll 2 dice, right? Like there's no other way unless my number skills are kind of bad. So, so there were 2 ways to, to get 11, but there were like 36 different combination outcomes possible, right? So the probability was just 2/36, which would be 1/18, right? So yeah, because of the 36, I mean, there were like 36 combinations, 6 from each die, but there are 36 combinations, and only 2 of those combinations gives you an 11, right? So the point is that in all these examples, like kind of like for the earlier probability problems we worked for, like the principle was kind of like, well, if you don't have any reason to prefer one thing over the other, then you should just go to like everything should count the same, right? In terms of probability, you just count it's like a question about counting, like every outcome is equally likely, and then yeah, the problem is just reduced to counting number of favorable outcomes divided by number of total outcomes, right? So that was like the probability of A, right? Like the probability of A was like the number of outcomes which would produce A divided by the number of total possible outcomes. And then again, for many problems, that's actually good enough, and it's like a good way to start getting just acquainted with probability concepts. But now, if you have noticed what we have been doing a little bit now when we're talking about random variables, we have been talking, well, maybe now you're throwing a coin, right, with heads or tails, but now the probability, maybe the coin is biased, right? So the probability is maybe not one half and one half, right? So we're saying now maybe the probability is just P, right? So now in this for random variables, we're dealing with many situations, where the outcomes may not be equally likely, right? Are not equally likely. Like for example, yeah, like the probability of getting cats, now we're calling P, right? And the probability of getting tails, now we're calling 1 minus P, right? And now P is not necessarily 1/2. P may not be 1/2. So the question is like, well, right. So there's a perspective you can just take, which is as well, let's assume that the probability is P, right? Which is one, let's say the probability is 1/3. So like one way to approach these problems is just to suppose that you know the probabilities, right? But it's like a more interesting question, like kind of more in practice, how you would think about these things in real life, which is like, well, how could you, like the better question or the more interesting question is how could you determine these probabilities based on some empirical data, right? So it is kind of, if you could somehow reconstruct the probabilities based on observations, that would be like an interesting thing to do, right? So that's kind of what we're going to discuss today, rather than just assuming that the probability had to be 1/3 or the probability had to be 1/5 or whatever. So for us, like kind of we're going to do today, like the reverse question, which is like, based on certain information, how could you infer what the probabilities had to be? Is that making sense? So and I think that's kind of like a useful idea because that's kind of like how statistics and other things actually would work in practice. Like maybe you cannot assume that the probabilities have certain values. You're kind of trying to figure that out as well. So for today, we're going to kind of discuss the reverse, right? We will discuss how to determine the probabilities of the events based on certain information that you have of them. The idea is that in general, the way to determine that it is using this principle, which is called the maximum entropy principle. So I'll tell you what that is. So this will use the maximum entropy principle. Okay. Okay, so for that, we have to talk a little bit about information or what's information. So before going first to discuss that, so let's give like a bit of information theory. So here, let's see, yeah, let's call E an event. So E could be like, for example, the sun comes out tomorrow, or tomorrow is raining. Okay. So E could be the Earth won't explode, right? Or the sun will come out tomorrow. or tomorrow will rain. Or what else could it be? That I'm going to get, the coin will land on a head. That's more close to what we have been doing. When I throw this coin, it will land on a head. It will land on a head, on heads, etc. So all of these, there are things that could happen, right? There are statements or propositions or events, however you want to think about them. And so you could think about how much information they carry if they somehow occur. So for example, so we're going to kind of give like a heuristic for what the information of this event should be. So let me write this as I of E. So this is going to be kind of like the information content of the event. So so what do I mean by this? So for example, imagine that the sun does come out tomorrow, right? And you tell that to someone, they probably wouldn't act as too surprised, right? Because like that's kind of like an event where you don't even worry too much about. It's kind of like baked into your daily life, right? Another way to say this is that the sun coming out every single day for almost all your life kind of makes you think that it has like just like a high probability of occurring tomorrow, right? So if someone said like, oh, you know, the sun comes out tomorrow, it's kind of like not something that you think it's not a statement that you may necessarily be too information, like, you know, in terms of content, it wouldn't be too much information worthy, or it wouldn't carry too much information because it's kind of something that everyone expected, right? In fact, like kind of like that's kind of how the news media operates, right? So there won't be a headline in any newspaper, right, ever like that says like the sun came out, because it's not new. Why would people say it's not newsworthy, right? It wouldn't be newsworthy because everyone's kind of betting on it, right? But if someone said, oh, there's like what would be an event that would be newsworthy? Maybe if there's like an earthquake tomorrow in New York City, which is very high, that would be newsworthy because maybe that's not something people were expecting to occur, right? So what I'm trying to say here is that you should think about this information kind of as what would make an event newsworthy in a sense. So it's kind of what makes an event newsworthy. And so from this perspective, what I'm trying to say is that the more probable an event is, just from this angle, the less information it carries, or like, because it's kind of like the less surprising it is, right? So it's kind of you are learning the least from it. So you kind of learn more from things that are more unexpected from this perspective. You know, there are other perspectives you can take, but the heuristic is that the more likely an event, the higher the probability an event, the less you learn from it, kind of, or the less surprising it is. So the higher. I'm not sure if someone is asking something or someone is just not muted. The higher probability of an event, the less information the less information it carries. Is that making sense? Just from this perspective, or the less surprising it is, if you want to say it that way. So far, so good. Is that kind of making sense? So I'm just saying, like, just trying to quantify the information something could have. And so I'm just saying, from this perspective, like, the more likely something is to occur, the less information it carries because kind of you saw it coming. So you're not like, it's not something you would pay too much to learn if you think about actually assigning money to it, right? People pay for secrets or things like that because it's kind of like, interesting stuff where like there can be like, it is less certain what's going on. But with more certain, the more certain an event is, kind of like people would kind of, the more quickly they lose interest in it. So what I'm trying to, the reason why I'm saying this is that the idea is that we're going to assign like a number to the information of an event. So the information of an event is going to be a non-negative number. Like that's like the fact that it's non-negative is more like a convention, I suppose. But well, in fact, it can be. Let's see. Should I want to say that? Well, no. Yeah. Like the information of an event is going to be. So it's going to be a non-negative number. So this is going to be a non-negative number. So the first criteria that this should satisfy, the first condition is that if probability of E equals 1, right? So again, you should kind of think if something has probability 1 as more or less occurring with certainty. So if the probability of E is 1, what's the information that you would assign to it? Like, again, kind of think of it as an amount of newsworthiness it has, right? So the event could even be like something silly, like you get either cats or tails on this coin, right? So what should be the amount of information or newsworthiness you assign to it? What do you think? Yeah, it should just go to 0 because again, if saying that, just think about it really like in this metaphor analogy of like writing an actual headline on a newspaper. There will never be a headline. The front cover of the New York Times is never going to say, if you throw this coin, you will get either heads or tails. It just because it just has like, but it could be interesting, interesting headline maybe. And that's kind of why Powerball or these lottery tickets are always fun to, people pay attention to them because it's kind of like someone winning it is a very low probability event. So it's kind of it's very information dense if that happens, right? And you would be happy yourself if you win the lottery. So I'm just saying, like, the less likely an event is from this perspective, that the more degree of surprise or the more information it carries. So in the extreme, where where the event is more or less certain to occur, then you should kind of say, oh, you don't gain anything new by knowing about it. So you kind of assign probability. You would like to say that the information is the the information this message carries is 0, and the other so this is like a useful constraint, and the other useful constraint is what happens if the events are independent, right? So if two events are independent, right? Well, remember in terms of like no, like the fact that two events were independent, well, that meant in terms of the probabilities, the probability of E1 intersection E2 was probability of E1 times the probability of E2. But like more like philosophically, that means that, like, knowing that one event happened does not increase or decrease the chance of the other event happening, right? So you could ask, well, what's the information, right? What would be like the information for the intersection of these two events, right? Um, so how can, if the events are independent? So here you have to think a little bit of what you would like to see occurring, right? But what do you think could be like a possibility? So it's kind of like how much information you're gaining if two events do not kind of are, how much information would you be gaining if two events took place, but they are not, they're kind of non-interacting. They don't, they kind of are separate things. Like, no, it's kind. You have to be careful because here it is like, for example, like you could think about, let's see, what is a let me see what would be a good example that uh, I mean, you could say tomorrow, right? Like one event could be tomorrow it's going to rain and tomorrow there's going to be an earthquake, right? You would think that those events are independent of one another, and like here I'm thinking because maybe one does not affect the other, right? Like there being rain seems to have no effect on whether there's like an earthquake and vice versa, right? So if you figure if tomorrow it happened to rain and it happened to have there happened to be an earthquake, right? I'm just asking like how much would that information, how much would the information of that be that you gain, right? Is that making more sense? But it would be weird to say that you gain no information, right? If the two happen tomorrow, so it cannot be zero because of that. Uh, any other guesses? It's closer to that, but here you also have to be careful. I mean, it is a reasonable thing to think, but it works a slightly different way with information. It's not the same as probability. Um, it is, well, it cannot just be like a specific. We don't want it to be a specific number just because it should be the sum because okay, think about it like in terms of knowledge that you gain. If you somehow knowledge could be like some sort of stuff, right? Like a substance that you kind of put in your brain. I'm kind of saying like the information that I gain from knowing that there's an earthquake tomorrow and knowing that tomorrow is raining is kind of they just add up together because like the events are independent. So it's or like and this would be like a better analogy like the memory that you would need to like store in the computer, that it rained tomorrow and that there was an earthquake kind of would be like the sum of the individual memories needed. So it's actually the convenient thing. It is more like to put it as a sum. So like actually like the information of an intersection in the independence case ends up being like a sum. Uh, And then here's a beautiful thing. This is another reason why the book, if you have been reading the book, they write the intersection as a product. There's many reasons why an intersection is kind of like a product, because if you think of propositions, like in terms of truth values, like true being one and zero being false, right? An intersection is only true when both are true, which is kind of like 1 times 1 equals 1. But if you do 1 times 0 or 0 times 1 or 0 times 0, you get 0. So like in a sense, like the intersection is kind of like a product. And again, that can be made more like a more precise. So it's kind of saying that the information, whatever this is turning multiplication into sums. And there is a function from pre-calculus that turns multiplications into sums, right? What's the function that turns multiplications into sums from Calc 1 or pre-calculus?
Is it sort of like when you multiply two exponents to each other, something like that? Maybe?
Well, if you multiply two exponents to one another, you're
I guess the
getting
powers get added, but
right. The powers are the things that are add. So it's kind of, I'm asking what turns like a product into a sum. It is a natural, I mean, it's a logarithm, right? Because logarithm of a times b equals logarithm of a plus logarithm of b, right?
yeah,
Log of ab equals log of a plus log of b. So essentially, based on, and you can show, it's kind of like a fun proof to show that basically up to a constant, like the logarithm is the only function with this property that it would turn like an argument which is written as a product into the sum. Like it's only more or less like the only function with property. So based on that analogy and the fact that logarithm of one, what's logarithm of one is 0, right? So based on that, you define the information of E as minus the log base 2 of the probability of E. So this is the definition of information. Why? Okay, let's see if this makes sense. Why the fact that instead of using natural log, I'm using logarithm base 2 is just like literally then if you want computer science applications for this concept, you want to measure it in bits. So this would actually give you the amount, this is interpreted as the amount of bits kind of needed to describe the event, kind of. I mean, I may get to more of that later on, but so this is related. So this, like the base 2 is just to use like the unit of bits. And notice that since since logarithm of and logarithm in base 2 of 1 equals 0, so that satisfies condition 1. And for independent event, like the logarithm of base 2 of the probability of E1 intersection E2, right? Since the probabilities multiply, you get like the logarithm of P of E1 times the logarithm of P of E2, and that's why it splits. So it does have like the sum property because of what I was saying. And while you put like a minus sign, it's just to remember like probabilities are between 0 and 1. And so between 0 and 1, the log in any base is negative. So this is just, the minus sign is just to make this quantity positive, right? So just, it's more like, it's better, it's kind of more useful to think of information as being positive than negative. Psychologically speaking, we're more used to negative numbers, to positive numbers. So just to make this just to make it positive, since the probabilities are between 0 and 1, right? So the argument of log in these problems is always between 0 and 1, and that's where log is negative. So you multiply by -1 and then you get something positive. Is that making sense? Is that okay? So for example, here's an example. So just to make it more concrete, here's a nice example. So you have a fair coin, right? You have a fair coin. And then you could ask for you could ask you E could be like, you know, E could be getting two heads, or, you know, if you have a fair coin which you throw twice, right? So which you throw twice. So E could be getting two heads, right? And so you could, what's the probability of getting two heads if you are throwing a fair coin? Or what is its probability?
1/4.
It's 1/4, right? Because it's heads, heads, and therefore possible outcomes. Heads, 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 tails, heads, or tails, tails, right? So it's 1/4. And so what's the information of this event? Is minus log base 2 of its probability. So it's kind of minus log of base 2 of 1/4, right? So what is, for those, I don't know, who are taking discrete math or whatever, I'm sure like you're working with log 2 many times. So this is minus log 2 of 2 to the -2, right? So what does that give you? What do you get? It's just 2, right? Like this number is just 2, because the -2 comes out. With this minus becomes 2, and log base 2 of 2 is 1, right? Is that making sense? So it's, the information is 2 bits, which means like if you wanted to write that you would require 2 bits to store this, so the 2 bits could be 1, 1. So the 2 bits could be 1, 1. To describe it, like a bit is something that just can take 2 states, like 1 or 0. So you would require a 1 and a 1, which is like the same saying cats, cats, right? Like, so it's kind of redundant. But that's like one way to think about it. Okay, and okay, so this kind of like to give you an idea of what this information is. And from once you have that, you can define what's called the entropy of a random variable. So like, and that's kind of one of the most important concepts in probability theory. So you have like a random variable which can take values x1, x2, x3, x4, etc. So here you have a random variable which takes values x1, x2, x3, x4 up to xn. So for example, if your random variable is the results of a die, x1 would be 1, x2 2, x3 3, and so on, right? Example, if x is the number, the result of a die, of throwing a die, you could take x1 to be 1, x2 to be 2, x3 to be 3. Of course, like in practice, I mean, in practice, like they're not so easy. The values could be other ones, but this is a particular case. Okay. So each value, let's say you assume that the probability that x takes the value xi is just pi. So you take pi to be the probability that x takes the value xi. And then the what's called the entropy, the Shannon entropy, is defined as the expected value of it's like an average of the logarithms of. I mean, this is kind of like an event. Maybe I should just to connect it to the previous to the previous discussion. This is kind of an event or an outcome, like the fact that x took a particular value. So the average or the expected value of all these events, of the information of all these events, is kind of like the defined as the entropy. So E1, E2, up to En are the some events, and the expected value of or I prefer the word average. Well, let me put both. Of these is defined as the entropy. Entropy of X. So what I'm just trying to say is that the entropy of X, you can just start from this definition that I'm about to give you. It's just the sum from I equals n, I equals 1 to n of pi times the information of ei. Okay, but this is the sum from I equals 1 to n of pi times minus logarithm in base 2 of pi. And yeah, that's how you end up, sorry, just to go up, yeah. That's how you end up with this definition for the entropy, which is like, if you look at the PDF, one of the problems that I had recommended for the quiz is kind of how you come up with this definition. I'm about to do some examples computing entropy so that you can see how it looks like. And so this is called the Shannon entropy. So it's kind of like the entropy is kind of like the average amount of information that the variable x, that the random variable contains. So this is kind of heuristically, it's like kind of like the average amount of information that x contains. I mean, again, there's kind of like the thing is like this quantity entropy is used a lot in communication theory. Like, how do you send a message across a channel? Like, like how do you, when you text them, imagine that you have on your phone, you're texting a message, like you're sending this. Okay, you are texting a message to a friend. That message has to be carried across like a channel. I mean, in this case, a channel could be like the electromagnetic. You have to think of how the messages are sent in practice. But in back in the day, like I guess when like the phones were like were connected to a cable, like you could imagine that there was like an electric signal traveling through that cable or whatever. So that's kind of like a channel where the message is being carried, and then this is kind of related to, if the channel has like noise, which is another way of saying that sometimes like the message is not, from time to time, like there will be like an error when you're transmitting the message, you want to design ways to minimize the error as much as possible. In order to do that, you have to kind of get into a discussion of what this Shannon entropy is. So it's kind of related to, like how to encrypt messages, how to decode them, how to send them with as little error as possible and things like that. So this entropy is kind of related to the number of bits required to describe the random variable. But I don't want to get too much into that because that's more like for, I guess electrical engineering or something like that. But there's something that's useful of that idea, which we'll talk about in a couple of minutes. But it's kind of related also to the average number of bits needed to describe a random variable. Okay, and this entropy, I'll tell you a little bit later, is also related to the entropy that you may have seen before if you have taken like a thermodynamics class. I don't know if you have, but so yeah, it's kind of there's a relationship with that. So it's kind of related to this entropy concept that in statistical mechanics and statistical physics gets used a lot of time. In the second law of thermodynamics and all that good stuff. So let me give you an example. So let's say that X is a Bernoulli random variable. Let's do something very simple. So X is a Bernoulli random variable with parameter P. So what did that mean? It meant that X could be 1 or 0, right? And X can take values 1 or 0. And the probability that X was 1, right, was P. And the probability that X was 0 was Q, which is 1 minus P. Is that making sense? Everyone remembers this? So this was like the Bernoulli random variable. And so what's the entropy of a Bernoulli random variable? So now we can find the entropy. Let's find the entropy of a Bernoulli random variable. So again, the entropy of X is just minus the sum from I equals 1 to n of the probabilities times the natural log in base 2 of the probabilities. So this is like, you can think of this as a first probability, and this is the second probability, right? So there are two probabilities in this case, which before I was calling P and Q, and I'm going to call P1 and P2. So it would be minus P1 not log in base 2 of P1 minus P2 log in base 2 of P2. So that's the formula for the entropy. But then again, now you can, if you want, go back to the previous notation. So it's minus P log in base 2 of P minus Q, right? Log base 2 of Q, but it's better to think about it as a function of P alone. So let me write it like this, because Q is 1 minus P, if you remember. Is that okay, everyone? Is that making sense of how I found the entropy for this variable, for this random variable? Is that okay is that good? So now this depends on P, right? So you can think of this as a function of P, right? we can think of this as a function of cop1 of P, depends on the probability of getting heads. So you can go to GeoGebra, you go to your favorite graphing thing, and let's plug it, plot it. So I don't know if on GeoGebra you can write not log in base 2, but it's easier just to put it in natural log because they just differ by an overall constant. So the shape of the graph is essentially the same. There's just like it qualitatively will look the same. So I'm just going to put natural log because it's just easier for me to enter it here on GeoGebra. There's okay, now I hate it when this happens. Okay, now it's fixed. So okay, good. Okay, so no, this is fine. So I'm going to put I only need P to go from 0 to 1 because probabilities only go from 0 to 1. So I'm going to put minus P ln of P. Let's see if this understands it. And if not, I will just change it to X because that may be better for GeoGebra to understand. Yeah. So it will, yeah, I have to use the letter X, but I mean, it's the same. And again, natural log it doesn't matter too much whether you use natural log or log base 2 for understanding like the graph. It's qualitatively the same.
Professor, I noticed an interesting thing on this graph. Like even if you don't set the input, like you don't restrict it to 0 to 1, it still just does that on its own too. I guess it's
if I don't restrict it to 0 to 1, sorry, what were you saying?
No, I was just saying even if you don't restrict like the input, it still is only like, I guess it only exists from 0 to 1 because if
right. Yes, yeah, I get you. Yeah, like right. Like because there are two variables. Yeah. Like 1 minus X. For that to be well defined, you need 1 minus X to be positive, so X has to be. Yeah. I get you. Good. But in general, right? Like that's okay. And so you have this very nice function, right? Which is what can you say about this function? Like anyone remembers calc 1? Is it concave up or concave down? It's concave down, and it actually will have a max. I mean, it's kind of pretty clear here that it has a max. And where is that max according to this graph? The max should happen at 0.5, right? So let's just check that there is a max. I mean, of course, to check that there's a max, you would have to use a second derivative test. I'm just going to be lazy and just find the critical point. And I mean, you can show in general the entropy has to achieve a maximum. So of course, you could do the second derivative test for that. But it's kind of, to I mean, now that we have the max is kind of clear. The graph is kind of clear, but yeah, like in general, if you wanted to do all the process, besides finding the critical point for this function, you would use a second derivative test or something else to show that it does yield a max. But I will just find the critical point for saving us some minutes. So what's the critical point here? So you have to find the first derivative, set it equal to 0. So what's the first derivative here? Well, I have to use the product rule, right? So the derivative of the first one with respect to P is just -1. So you get minus L log 2 of P. And then minus P. What's the derivative of log base 2? I mean, it's more or less the derivative of natural log. There's an overall constant between them. So it's P times ln of 2. So that's what you get like when you take the derivative of the first term, and then you do the product rule again on the other one. So you have to be a little bit more careful here. So it's -1 log base 2 of 1 minus P, and then -1 minus P. Again, 1 minus P log base 2. Sorry, natural log of 2. And the derivative by the chain rule of what's inside is this. Okay, So it is the derivative is not as bad as it seems. I just need to simplify it a little bit. So the derivative is minus log base 2 of p, right? This cancel out, so you get minus 1 over ln of 2. And then you get right, it's like plus 1 plus log 1 or minus p. And then okay, there are a bunch of minuses here. So let's see. Oh, this cancel again, right? And then minus becomes a plus. Oh, excellent. So 1 over ln of 2, right? Good. So these two are going to cancel out, right? So you just get log base 2 of 1 minus p minus log base 2 of p. I mean, I prefer to see, I guess, this one with this one in the second term because it appears with a minus, and then if you want, you can just like put them together as a single argument, and you want this to be 0, right? When is a log 0? The log is 0 only when the argument is 1. So you need 1 minus p over p to be 1, right? So you need 1 minus p to be p, so you need p to be 1/2. Is that making sense? So that means that of all the Bernoulli random variables, the one that has maximum entropy is the one where the coin is fair, right? So a fair coin is the one that maximizes the entropy among the Bernoulli random variables. So among the coins, right, or among the Bernoulli random variables, the fair coin yields, or the fair case, maybe I should say that the fair case where p equals 1/2 maximizes the entropy. So far, so good. Is that making sense? So in the general case where like it's not just two outcomes, right? Because in the Bernoulli case, the two outcomes were 1 and 0. In the general case, so in the general case, X has n outcomes, not just 2, right? X1, X2, Xn, with probabilities P1, P2 up to Pn, right? And the entropy of X was minus the sum of I equals 1 to n of Pi log of 2 of Pi, right? So my claim is that in this case, the values of the PIs which maximizes the entropy is a case where all the PIs have the same value. So here's my claim. Because maybe I should say this first. Like this, you can actually think of a function of P1 up to P1, P2, Pn. So think about it as a function of multivariable calculus. This is why multivariable calculus was a requisite in this class. So this is a function of P1, P2 up to Pn, multivariable function. So my claim is that the values that maximize this function f has a maximum when P1 equals P2 equals P3 when all the PIs are the same value and it's 1 over n. So f of p1, p2 up to pn has a max when all the PIs So the same kind of the case of maximum entropy or the case of maximum information gain is when everything is equally likely. So entropy is maximized when all the outcomes are equally likely. So let's just to do this quickly. Let's find the critical points of this function. Again, you could check that this is a max. This will yield a max, but it's just for the sake of time. And also, yeah, probably in calc multivariable, you only saw the second derivative test for 2 variables. So this is a little bit more tricky. So I'm just going to check that it has the critical point occurs where all the PIs are the same. So let's just find the critical points. Of f of p1, p2 up to pn. So how can you find the critical point of a function of several variables? Anyone remembers this? What was the critical point of a function of 2 or 3 or 4 or 5 variables? When does that occur?
Did we have to compute like the partial derivatives, like the mixed partial derivatives, do like the Hessian, some?
Well, the Hessian is needed to classify them. Correct.
I see.
The Hessian, because the Hessian, if you remember, I'm glad that you still remember the good old Hessian. The Hessian was a matrix of second partial derivatives, but the second partial derivatives are always only used for classifying the critical points. You don't need them to find the critical points, right? What was the definition of the critical points? It had to do with the partial derivatives, right? So what did we require about the partial derivatives?
I think you set like all of them equal to 0, like.
Right. A gradient was where, okay, the partial derivatives have to be equal to 0, or if you prefer, the gradient has to vanish, right? Because the gradient was a vector made out of partial derivatives, right? Anyone remembers this? Okay. The gradient of f was the partial derivative of f with respect to p1, partial derivative of f with respect to p2, blah, 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 partial derivative of f with respect to pn. You probably only did this for functions of 2 variables in Calc 3, and most 3. I don't think you would ever do functions of more than 3 variables to find the critical points. But the critical points of a function of multivariable calculus is just set each partial derivative equal to 0, right? But here's a catch in this case. What's the catch in this problem? There is a more subtle point that's happening here. Because the probabilities are not arbitrary, right? There's something that's happening here. There is what you would call a constraint in Calc 3. What's a constraint that you have here? Like, what's the constraint? Because what is something that must be true about the probabilities? What happens? Like, for example, before P and Q were not independent, right? Because if you knew P, Q was 1 minus P. So P and Q were not 2 separate independent variables, right? So in this case, the probabilities, well, it's going to be a Lagrange multiplier problem, correct? Because there's a constraint. So we're trying to figure out what this constraint should be, right? I'm saying that the probabilities, the numbers are not independent of one another because there's a property that every probability must satisfy.
Has to be normalized.
Right, they must add up to 1, right? So P1 plus P2 up to Pn must, but P1 plus P2, Pn are not independent. Blah, 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 blah. Pn are not independent variables. Since the sum of the probabilities must add up to 1. Is that making sense? So this is a constraint equation, right? This is what in Calc 3 you would call a constraint. So you actually, to find the critical points, you need to use the Lagrange multiplier method. I mean, this constraint is very easy, so you could solve for one of the variables, but it's so not elegant. It is more elegant to do with the Lagrange method. The Lagrange method is actually way better because soon we will do like a small upgrade to it. So we must use the Lagrange method. So in the Lagrange method, we didn't ask for the gradient to vanish. What was the condition? Instead of the gradient vanishing, what did the gradient have to be? I don't know how long ago you took Calc 3. So,
Lambda
I don't know.
times the gradient of G.
Right, it had to be the lambda times the gradient of G. So you can call G all this function, giving you the constraint. So it had to be lambda times the gradient of G. Perfect. Just give me a second. So you need to solve the gradient of f has to be lambda times the gradient of G. It is the good thing is that these functions are very simple, so it's easy to find each of the reason why they're simple is because like if you look at these expressions, the kind of like the variables are not being are kind of appearing separately. They're not you know, you don't have an expression where it's P1 times P2 or something like that. It's P1 only appears on its own in some function. So that is what makes it slightly easy to work with. So you actually need, so this meant, so the gradients being equal just meant that the partial derivative of f with respect to pi has to be lambda times the partial derivative of G with respect to pi, right? But where I equals here 1, 2, 3 up to n. So what's the partial derivative of f with respect to pi in this case? Well, it is kind of like the product rule that we were doing before. So I can just simplify it a little bit. You get minus log 2 of pi if you apply the product rule, and then you get minus 1 over ln of 2. That's what you get. That's a partial derivative with respect to pi. That's what you get there. Okay. Okay. Yes, that should be fine. And if g of p1, p2, pn is just p1 plus p2 plus p3 up to pn. So again, this gradient is very, this partial derivative is very easy. The partial derivative of g with respect to one of the variables is just 1. So these are not too bad. So really what you have to solve for each I is the minus, so you need to solve the minus, so the Lagrange equation becomes minus log base 2 of pi minus 1 over ln of 2 equals lambda. Okay, is that making sense? because it's lambda times 1. Okay, I could put lambda times 1 if you prefer. So it is, that's just what the Lagrange equation is. So that means that mine, or if you prefer, minus 1 over minus lambda over 2 minus 1 over ln of 2 minus lambda equals a log of 2 of pi. So I just prefer to have like the logarithms with positive coefficient in front of them. So it gives you that. Okay. Is that making sense how I found this so far so good?
Professor, just had a question. When you did like the function g and you like sum them all up, is that like from the sum of like pi is equal to 1? Is that where you got that from?
Right,
Okay.
because like because like the probabilities must add up to 1, right? So it's just I mean, I could have written this for like, imagine that there were only 3 probabilities, right?
Yeah.
3 outcomes. So case n equals 3 is like that P1 plus P2 plus P3 would be 1, right?
That makes sense.
And that's a constraint. In fact, that's the equation of a plane, because it is kind of like x plus y plus z equals 1, right?
I see.
So it is like the constraint equation is actually always a plane or a hyperplane in the probability space. If you think of like a probability, each probability as being an axis, this gives you like the equation of a plane. So it's kind of like you're maximizing this function subject to the constraint that the points must lie on a plane. In fact, it's a little bit less than a plane because the probabilities cannot be negative and greater than 1. So it's called what's called in mathematics a simplex, which is kind of like a triangle, roughly. So it's kind of like what you would get in top 3 if you did like the intersection of the plane x plus y plus c equals 1 with the first octant. You would get like this piece of triangle. That's kind of like the analog of what happens when there are more outcomes. It's like an analog of that triangle in higher dimensions.
I see. That makes
so
sense.
it's very cute.
Go ahead.
So is that making sense? So the cool thing here is that this doesn't depend on I, right? This is the same value for every single I, right? Where do you see an I here? Nowhere. So the same for every single I. So that means that the logarithm of in base 2 of P1 has to be the logarithm in base 2 of P2 has to be the same as the logarithm in base 2 of P3, etc. Because each of these is separately equal to this quantity. So that means that all these logarithms are the same. And how can that only happen? That can only happen. No, the probability cannot be less or greater than 1. So what I'm saying is that if you ignore, like what I'm saying is that if you have like an axis P1, P2, P3, right? The constraint, this constraint would just be a plane if you ignore that restriction. But because the probabilities are between 0 and 1, you don't get like the full plane. You just get like what's called a simplex. So you don't, the constraint equation is not like the entire plane, or it's just like a piece of the plane, the piece where like the probabilities satisfy the restrictions that they are between 0 and 1. Is that making sense? I'm not sure. Did I answer your question? I'm not sure. So yeah, if there were no more restrictions, this equation would be the equation of a plane. But because the probabilities are between 0 and 1, it is not the full plane that you get. You just get a piece of the plane, which is what I'm drawing right here, like the piece of the plane that inside the first octant where like the probabilities lie between 0 and 1. That's what is. This triangle is usually called a simplex, but the name doesn't matter. It's just like a triangle, right? So like the Lagrange multiplier method is actually taking place over a triangle. But or like if you prefer, like maybe it's easier to draw it in two variables. When it was two variables, when P1 and P2 are equal to 1, yeah, is the the optimization problem. If you had done, you can also do this one as a Lagrange multiplier problem. It's kind of more elegant. And I'm just saying like the probabilities are, this is the equation of a line in terms of P1 and P2, but because the probabilities cannot be greater than 1 or smaller than 0, it is not the full line that you get. It's just this segment, right? Is that making sense?
Yeah, it does.
Yeah, so it's just yeah, that's, but I'm just saying for the purposes of finding the critical point, that's more or less a subtlety that doesn't affect it. It kind of works the same way. So I'm just saying, like, once you know that the probability, that the arguments, that all these logs are the same, that forces all the probabilities to be the same.
Just like one
And so that's
question.
uh-huh.
Sorry, might be a little silly, but the partial derivative of g with respect to pi is equal to 1 because each one is just like p1 plus p2 plus p3, right?
Correct. Yes. It's
Okay,
like it just looks weird because maybe you're used to
Yeah,
writing it in terms of x, y, z. But if I
exactly.
told you what's the probability, what's the derivative of g with respect to x, that's just 1, right?
Mhm.
It's just that now I'm calling the variable p1, p2, p3, right?
I see.
So, but it is the same. By analogy, it's kind of the same.
That makes sense. Yeah, I was
Right.
getting confused because the sum of the probabilities is also 1, but that makes sense. I figured it out.
Yeah. So good. So this but now you use the fact that the probabilities have to add up to 1. But if they're all the same, so that means that you can call this p. So that means that np equals 1, and so p equals 1 over n. So that's how you get the critical point for the entropy happens when all the probabilities are the same, and that means that the entropy is maximized when everything takes the same value. Is that making sense? So far, so good. So why am I doing this? Because so what I was saying at the beginning of today's class, that if you had no information, the easiest thing to assign was equal probabilities to each outcome can now be said as, if you don't have extra information, if you don't know anything about the problem except the certain outcomes are happening, you should just assign the distribution or the probabilities that maximize the entropy, right? So the probabilities that maximize the entropy is where everything is equally likely. So if you don't know anything else about the problem except that there are 2 outcomes or 3 outcomes or 4 outcomes, then you have to choose the option that the entropy is maximized. And so what I'm going to do like a quick mini break of 5 minutes, because this will be the last part for today. So the extension of that principle, which is called the maximum entropy principle, is that if you have extra information about the random variable, you should still choose the probabilities that maximize that entropy, subject to the new information about the random variable. So again, this is kind of sounds a little bit weird. So I'm going to show you how this looks like in a moment, but that's essentially how you find this probability, this Maxwell-Boltzmann distribution of statistical mechanics. So I'll tell you how to get it just from the entropy principle. And that's kind of like, how you start deriving properties of like thermodynamics from a statistic, like making assumptions about the particles and things like that. So using this maximum entropy principle. So let's just take like a quick 3-minute break or 4 minutes, and I'll tell you quickly how to do this in the general case. Okay, so I'll tell you now about the maximum entropy principle. So this is this idea, I think, I mean, probably has a longer history, but at least stated in this way, was stated by James. But yeah, I mean, like a version of that probably is more or less what Boltzmann and other physicists had in mind. But here's like an example, just to show you the sort of problem that I want to discuss right now. So imagine you have a die or a fair die. So like you have like the random variable, which is like what you can get on this die. So the random variable, what's the probability that X would be 1? It would be 1/6. The probability that X would be 2 would be 1/6, right? The probability that X would be 3 would be 1/6. I'm getting tired, but I'm going to do all of it. Right, because it's kind of like saying that if it's fair, that kind of we take as synonymous that each probability outcome is equally likely. And so what's the expected value or the average of X? It would be the sum from I equals 1 to 6 of well, X like I times probability that X equals I. Right, and so what is that? That would be, I mean, each probability is 1/6, so it's just 1/6 times the sum that from 1 equals 6 to 1 equals I equals 1 to 6 of I. So this is 1/6 of 1 plus 2 plus 3 plus 4 plus 5 plus 6. Right, so what's the number, by the way? That's 3.5, right? So the average, if you throw a fair die multiple times, the average should be 3.5, right? Is that making sense? So the average of throwing a fair die multiple times is like 3.5, the expected value. But now imagine that you have an experiment where you're throwing a die and you find that the average is actually behaving more like it's closer to 4 than to 3.5, right? So here's like a question. Now suppose that on an experiment, the average of throwing the die is closer to 4. So what should that suggest? Like, does it suggest that the die is not fair, right? So this suggests it's not fair. So not every probability should be equal to 1/6, right? So for this particular die, not every probability should be. So the outcome should not be equally likely. Is that making sense? So the question would be, what should that? So if the die is not fair, what should the probabilities be in this case? Like maybe they're not all 1/6, but so what should these numbers be? So how do you find the probabilities P1, P2, P3, P4, P5, P6, right? Is the question making sense? I'm just trying to make sure that this, even if the question is reasonable. So I'm just asking, what should be the probabilities that give you this average value for the die, right? And the maximum entropy principle says that you should choose the probabilities compatible with this expected value that will maximize the entropy. So the maximum entropy principle says that you should choose P1, P2 up to P6 in such a way that you get the correct expected value, that the average is what you know the average to be, in such a way that you get the correct average value, the average value that you know. So, and the entropy is maximized. So it has to be, in practice, what you have to do is maximize the entropy subject to all the information that you have about the problem. So when you have no information about the problem, the only constraint is that the probability should add up to 1, and that's how we find that all the probabilities are equally likely. But if you now have more information about the variable, like the random variable, like its expected value or its average, then you should maximize entropy subject also to the second piece of information. Okay. So let me make it more concrete. Here's like a concrete way to do it. So I can call PI the probability that X takes a value. So in the general case, call PI the probability that X takes the value X of I. And so what we want to do is to maximize the probability, the entropy of X, which is minus the sum from I equals n of PI log base 2 of PI, subject to what? To two things, right? The fact that the sum of the probabilities should be equal to 1, that's the same as before. And now the sum, the average is known, right? So it is so now what I'm trying to say is that the difference with what we were doing before, before we only had the question about maximizing the probability subject to this constraint. Now we're going to maximize the probability subject to two constraints, right? So there's a first constraint, let's call it G1. And the second constraint, G2, which is that the average should be this known quantity. And these are functions of the p's, so it could be confusing because usually the X happens to be the variable in most applications, but now the probabilities are the unknowns. Is that making sense? So what is this? It's a Lagrange multiplier problem again, but with two constraints. So now you get a Lagrange multiplier problem with two constraints. So I don't know. I'm definitely since I teach multivariable, I know that typically we would never do Lagrange in multivariable with two constraints, but I don't know if anyone ever bothered to read that section of the book that says what to do when you have two constraints in a multiplier problem. Do anyone remember? I don't know. Did everyone ever like bother to read that? Like maybe someone was curious. What should happen? So in the usual case, right? In the usual case, a Lagrange multiplier is just that the gradient of f, right, should be lambda, the gradient of g, right? What do you think happens if there are two constraints?
You have like two constants, right, in there? I saw like lambda.
Yeah, it's basically you just sum the constraints, like it's lambda 1 gradient of g1 plus lambda 2 gradient of g2, correct?
I remember
Yes.
I found one of these problems on Paul Online Math Notes. They're definitely way harder than the actual exams.
No, it is. And then, but okay, we can copy paste a couple of things because the formulas are the same. So we had found before the partial derivative of f with respect to pi, it was that minus log of 2 of pt of pi minus log of 2 of pi minus 1 over ln of 2. We also had g1 is still the same one, right? That's an easy partial derivative. The partial derivative of g1 with respect to pi was just 1, right? It is the same constraint as before. That's nice. And the other one is not too bad either because, again, here the x's are constants because you do know the values of the random variable. The only thing that you don't know are the probabilities with which those values are occurring. So it's kind of confusing because you're so used to thinking of the x's as the variables, but here the x's are constants. So if you take the partial derivative of g2 with respect to pi, the only difference now is that you find xi. Okay. So for so this equation, the Lagrange equation becomes minus log of 2 of pi minus 1 over ln log ln of 2. And that gives you what? That gives you lambda 1 times times the partial derivative. So it gives you lambda 1 times 1. So you get lambda 1. And then lambda 2 times the partial derivative is coming from this term. So you get lambda 2 times xi. Lambda 2 times xi. Okay, and you have one of these equations for each of I from 1 to n. So this equation is valid for I equals 1 up to n. So let's do the same as before. I can solve for, I want to have log of P2 as a positive constant. Sorry, as a positive quantity. So I'll move it to the other side. I'll move everything else to the left-hand side. Okay, and this gives you, okay, this is how can you solve this? Like you could solve this for let's see, so what's a log? I mean, it's better, it's nicer to look at have like the exponential function, like the natural log. So there's this change of base variable, right? So what is log 2 of x? What is it? is lateral log over log of 2. So let me put it like this: 1 minus ln of 2 minus L1. This is lateral log of pi over ln of 2. It's just that the exponential number is so much nicer. So you get -1 minus ln of 2 times lambda 1 minus lambda ln of 2 lambda 2 xi is ln of pi. And that gives you what? Where is mine? That gives you like a formula for the PIs, right? How do you find a formula for the PIs? You just exponentiate this term, right? So PI is e to the -1 minus ln of 2 lambda 1 minus ln of 2 lambda 2 xi. And this is for I equals 1 up to n. Is that making sense? But there are better, just to finish this, so there are a bit better ways to write it, because you notice that the first term quantity does not depend on I, so you can just use a property of the exponential to split it as a product. So this is e to the -1 minus ln of 2 over lambda 1 times e to the minus ln of 2 lambda 2 xi. Okay.
That's xi, right? Not lambda, right?
Oh, sorry. Thank you so much. Yeah. Good. Excellent. Glad. This number is too, my letters too small. So let's see. Stupid natural logs. Okay, this is an xi, I promise. So okay. But if you use now that the sum, now let's use the constraint that the sum of the probabilities should add up to 1. So if you sum these probabilities from I equals 1 to n, you should get 1. So that means that summing this from 1 to n should give you 1. So 1 should be equal to the sum from I equals 1 to n of e to the 1 minus ln 2 of lambda 1, e to the minus ln 2 lambda 2 xi. But this is a constant, like this doesn't depend on I, so you can pull it out. So, or another way to say this is a 1 over oops. Okay. Okay. And that gives you, as ugly as that looks, it actually gives you a formula for the lambda 1 implicitly, because then you can say this gives you like a formula that e to the -1 minus ln of 2 lambda 1 is 1 over this chunk. Okay. And so that if you plug that back into here, then you get the formula that I was after for the PIs. So you get the formula that PI equals e to the minus ln of 2 lambda 2 xi over let this sum. And this again is true for I equals 1 through n. Okay. So, by the way, like these quantities, what in physics is called like a partition function. So if you ever see that, it is what in physics is called a partition function. It is one of the most important concepts in all of statistical mechanics, but that's an aside. Like I don't want to go down to that rabbit hole. What is cool about this formula, I mean, it's like looks a little bit weird to interpret, but if it is better if you take the ratio of 2 of these probabilities, right? Because if you take the ratio of 2 probabilities, right, the denominator is the same in both, right? The denominator is the same in both, because this is a sum, right? So actually it doesn't depend on I, so this cancels out. So you just get e to the minus ln of 2 lambda 2 xi over e to the minus ln of 2 lambda 2 xj. So the ratio of probabilities is, you know, you can use a property that the ratio of exponentials is, you know, you just subtract the exponents, so you get e to the minus ln of 2 lambda 2 xi minus xj. Okay. And here's okay. Just and again, this is kind of like a nice application just to give you and like the way this is used, like, you know, the application of how this is used in thermodynamics, for example. So in thermodynamics, it just happens to be the case that lambda 2 is the inverse of the temperature of the gas. Like, so you have like a gas. So here's a gas with a bunch of molecules. So X now represents that it's like the random variable that gives you the energy that one of these molecules could have. So it's like the random variable representing the possible energies of a molecule inside this gas. Of a molecule inside this gas. At temperature T. And then lambda 2 is actually what's in that gets identified with what you call lambda 2 ends up being 1 over Boltzmann constant. Like maybe you have seen this if you have ever seen the ideal gas law equation. PV equals nRT, that you can rewrite in, I think that one you can rewrite in terms of Boltzmann's constant. So this is like KB is like what's called the Boltzmann constant. I mean, well, I guess I need ln of 2 lambda 2 ends up being that. There's like a bit discrepancy because I was working with log in base 2. In physics, you work with natural logs usually. So this is KB is like the Boltzmann constant. So the way in which you would write this, so the way in which you would write this is what like the physicists call the Maxwell-Boltzmann distribution for an ideal gas. I mean, you end up getting what they would call the Maxwell-Boltzmann distribution. So this becomes 1 over ABT, and xi, xj were just the values of the energies of the particle could take. So it's just like a subtraction in the difference of the energies. Okay. And if you think, for example, that the gas is all the energy is kinetic energy, if you make that say the simplifying assumption, like in the ideal gas law, because in the ideal gas, you assume that you have a bunch of particles which do not interact. So there's no potential energy, or you kind of like, you kind of play with that a little bit. So you can take the energy of the gas, like to be 1/2 the mass of the particle times the velocity squared, right? Only kinetic energy. You get that the probabilities are, is like the ratio of the probabilities are like 1 over the 1 over the inverse temperature, and then this the mass is constant, so you get mass over 2 VI squared minus VJ squared. Okay. So it gives you it more or less. With that, you can kind of start deriving a bunch of properties of like the equations of the thermodynamics. This is kind of one of the most important probability distributions in all of physics, all of nature, and the fact that it is quadratic in this in the velocity gives you a Gaussian. So we'll talk about a Gaussian distribution for probability once we get to the continuous case. And that's kind of how you get the bell curves to appear. So this has like it is like a bell shape if you, in terms of the velocity of the particles. So you kind of can start making a lot of connections with statistical mechanics if you just like use this maximum entropy principle the right way. And that's kind of how physicists use it. Like their idea is that in equilibrium, what they call thermodynamic equilibrium, the entropy is maximized. That's kind of the version of what they use of this maximum principle. So they're like in physics, like in thermodynamic equilibrium, the entropy is maximized. In physics. Well, I guess I just want, yeah, right. Like when I say statistical physics, like it kind of using it synonymous with statistical mechanics. I guess for historical traditions, like you call it statistical mechanics because that's kind of how it was first implemented. But yeah, if you say statistical physics, there wouldn't be too much of a confusion between the two. It's just that, yeah, I think it's more of a historical thing. That it was given the name mechanics, but it is like just applying methods of statistics to physics. So it's kind of statistical physics. This is what it's called like historically the kinetic theory of gases, when they were trying to reconstruct thermodynamics, like the physicists like early 19th century, like Maxwell, Boltzmann, all these people. Well, Boltzmann, I guess, was probably early 20th century, but like in this era, they were trying to explain heat in terms of like the molecular motion inside of the atoms inside a gas or things of that sort. So they had to come up with like a theory of like, since the number of molecules you were dealing with is so large, you cannot keep track of each individually. So you have to apply statistical methods to understand it. So Maxwell kind of was the first one, I guess, who came up with this probability distribution. But then Boltzmann kind of gave like a statistical interpretation of entropy, which is kind of related to this thing that I was telling you about. And then there was like a big thing about like, I mean, if you ever like, even entropy is kind of like a concept that appears from time to time in popular culture, because there's this famous second law of thermodynamics that the entropy increases over time. So it's one of the big topics in physics to understand like the nature of the second law. And things like that. So, but yeah, it's kind of just to show you that this stuff is, I mean, these problems of probability is more useful than just throwing dice, right? Or like, heads or tails. Like literally with these tools, you can start like describing the behavior of gases. You can start like studying actual material, like solid, like what's called solid physics, also like, behavior of like conductors or things like that. I mean, without statistical methods, like you wouldn't be able to develop any powerful physical theory. So it is just like for like pedagogical purposes easier to state things in terms of coins or like die, but it is literally the same mathematical tools that allow you to then derive the properties of gases, or like what chemists call like the chemical potential, all these like fun things that make thermodynamics useful. So I guess, yeah, like the entropy of random variable, I think is a fun, important topic, but I think this kind of actually gives a good idea of like what to do in the case that the probabilities are not necessarily equal to one another. So the philosophy is to find the probabilities, the values of the probabilities that will maximize the entropy subject to more restrictions. So that's kind of what we just did in this example. Of course, like this example was a little bit too complicated, and it's not that I'm expecting you to, even have been able to follow every single detail, but I think it's something you can remember, like, in 2 years from now or whatever, that this is actually useful for something besides just like throwing coins. It's just that that's easier to understand, but again, like it just does help a lot more. And again, this is also related to for those who are interested in electrical engineering, all this problem about how do you code a message to minimize the amount of error in the transmission of that message. I mean, this entropy concept is really powerful, has a lot of applications. It's probably one of the most important ideas in all of probability theory. So it's kind of at least good to see a little bit about it, but I wouldn't ask more beyond that, like kind of what we were doing a bit earlier today, like find the entropy of a Bernoulli random variable, like very basic things. I wouldn't ask you more than that. I wouldn't, because again, I wouldn't expect you to kind of find this distribution of Maxwell Boltzmann. But yeah, I think it does give you like hopefully a better idea of like how all these tools can be applied for more like interesting stuff. So yeah, I think like probably something like this is something more concrete, down to earth is kind of where I would stop in things that I would like you to compute. But it's kind of nice to see it like used for some more powerful things. Okay, yeah, but no, I think that's kind of what I wanted to say today. So just remember that there's the quiz for today. I turn it into an assignment, so you have until tomorrow to upload it if you want. Does that make sense? I'll see you on Monday. That's okay. You too. Bye.
Thank you, Professor. Have a good one.
Bye. You too.
Thank you, Professor.
Bye.
Thank you.
Bye. See you.
Thank you, Professor. See you.
Bye. See you.